The last topic in section 9.4 is how does one compute the arc length of polar curves? All right, so the arc length of polar curves. Well, the bottom line is you compute the arc length of polar curves by essentially switching it into parametric and then realizing how you can compute the arc length of a parametric curve. Recall that for parametric curves, we use a formula arc length s is the integral from a to b of ds, but we wrote ds as ds dt, where t is my parameter for my parametric curve, dt, and of course ds dt you should recall is the square root of dx dt squared plus dy dt squared. So, and early on in this chapter we learned how to write a polar curve in parametric form by using the fact that x is r cosine theta and y is r sine theta. Okay, so we could just do that, but the curious thing is there turns out to be a little easier formula if we do this in general. So if I'm on the polar curve r of theta, then this is a function of theta, and so is this. That's a function of theta, and so is sine theta. I've got a parametric curve in terms of the parameter theta. All right, so what's my formula say? The arc length is the integral of ds, which is ds d theta, where ds d theta is dx d theta squared plus dy d theta squared. Now, I could do that for any particular curve, but I'm going to do it in general. Okay, so dx d theta, remember x is r cosine theta. Both of those are functions of theta. So I'm going to use the product rule. Dx d theta is d by d theta of r cosine theta, which is dr d theta, the derivative of the first, times cosine theta, plus the first, which is r, times the derivative of the second, which is minus sine theta. I clean that up. Dr d theta is just r prime, so it's r prime cosine theta minus r sine theta. I do the same thing for y. Y is r sine theta, so dy d theta is, using the product rule, the derivative of r times sine theta plus r times the derivative of sine theta, which is cosine theta, and what do we end up with? R prime sine theta plus r cosine theta. Now, I'm shooting for what this inside thing looks like. So dx d theta squared is, I just take this thing and square it. Here it is squared out, r prime squared cosine squared theta, twice the cross product, minus 2r prime cosine theta sine theta, plus the last squared, r squared sine squared theta. And I do the same thing for dy d theta squared, and I get this ugly thing. But what happens when I combine these two? Which is what I'm going to do under the square root. Well, and the answer is this middle thing goes away. And in fact, the first term has a common factor of r prime squared, and the last term that doesn't go away has a common factor of r squared. So when I clean things up, I get r prime squared times what? Cosine squared theta plus sine squared theta. Wow. What is that? That's just 1. And then if I factor out an r squared, I get r squared times sine squared theta plus cosine squared theta. Wow. Again, what's that? That's just 1. So what is dx d theta squared plus dy d theta squared? It simply is r prime squared plus r squared. Now, isn't that nice? And in which case, then s, which is the integral of ds d theta is, well, this inside I just shown is r prime squared plus r squared. d theta. And that, my friend, is a formula for the ages. Okay, so in fact, let's kind of highlight that. That is our formula for arc length. All right, let's look at a particular example. Suppose I want to find the arc length of the curve r equal 2 cosine theta. That's one of my favorite curves. Theta runs from 0 to pi. You should realize again what? That's a petal curve, one petal. That's a circle. As theta runs from 0 to pi, I trace that circle out exactly once. But let's see how we apply the formula. So the arc length is, okay, theta runs from 0 to pi, so I go from 0 to pi of the square root of, what is it? R prime squared plus r squared. Well, there's r. So what's r prime? It's minus 2 sine theta, all squared, plus r squared, which is 2 cosine theta, all squared. And now clean it up, I get what? 4 sine squared theta plus 4 cosine squared theta. I can factor out a 4 from both those. What's left is sine squared theta plus cosine squared theta, and that 4 was inside the square root, so it comes out as 2. This thing is just 1. The square root of 1 is 1. I end up just integrating 0 to pi of 2 d theta. And of course, the integral of 2 is 2 theta. Evaluate between 0 and pi, I get, what, 2 pi minus 0, which is 2 pi. All right, I chose to do an example whose arc length we could already compute. How? Well, this is a circle. What's its radius? Well, I can tell you that its diameter is 2. Here's a picture of it down here. The diameter is 2, so the radius is 1. Hence, that's a circle of radius 1. And if we integrated from 0 to pi, we've gone around it exactly once. So what is the arc length of this curve? It's the circumference of a circle of radius 1. But what's the circumference? 2 pi r, but r is 1, so I would get the circumference, which is this arc length, to be 2 pi. And I get a warm fuzzy feeling because that's what I got up there. Bottom line is, if you want to compute the arc length of a polar curve, r as a function of theta, this is the formula to use, and you have to integrate from whatever angle of theta to what other angle of theta is that you want to find the arc length of. Well, that in fact finishes up section 9.4. Have a good day, and bye.